Okay, so the last thing that I want to discuss is eigenvectors. Some of you may have seen eigenvectors on your A-level further math syllabus. Some of you may have not, but regardless, I mean, I definitely didn't. Eigenvectors are quite simple to calculate, so I thought I'd just quickly go over it. So if we have a two-dimensional plane like this, if we have a matrix, for example, let's have a matrix A, and we'll set this equal to 1, 1, 0, 2. So if we have a vector on this two-dimensional plane, when we apply the matrix A to the transformation, if we apply the matrix A to the vector, it will end up somewhere else on the two-dimensional plane. So for example, I could have a vector U, for example, here, and after the matrix A has been applied, it may point in a completely different direction. So for example, maybe here. But eigenvectors are, well, each transformation matrix has its own special set of eigenvectors, and simply these are vectors that stay on their span after being transformed. And what it means by staying on your span in terms of vectors is that the vector will point along the same line. So for example, if I have a vector v pointing like this, if I then apply the matrix transformation A to it, and v is an eigenvector, then the vector v will point along this line. So for example, it might end up here. This might be v dash. As you can see, the transformed vector v still points in the same direction as the original vector v, but it just has a different magnitude. The transformed vector can also point in the opposite direction. So for example, the transformed vector v could also be this blue vector. And the way that we can calculate eigenvectors is using this equation. So if we have the transformation vector A, we can say that A multiplied by V is equal to lambda multiplied by V, where V is the eigenvector and lambda is called the eigenvalue. Eigenvalue. And so this eigenvalue is just a scale factor which the vector v will be multiplied by. So some of you may think that, oh, we can just take the lambda v over to the other side and then factorize the equation, but we actually can't, because on the left-hand side we have matrix multiplication, but on the right-hand side we have scalar multiplication. So to fix this, we could rewrite the right-hand side as lambda I multiplied by v. And if we remember from before, I is equal to 1, 0, 0, 1. And so this will be equal to lambda 0, 0, lambda v. Now we can take the matrix over to the other side, and we will get AV minus lambda 0, 0, lambda v is equal to 0. If I then factorize the left-hand side of the equation, we will get A minus lambda 0, 0, lambda v is equal to 0. And notice that the vector v has to be on the right-hand side because matrix multiplication is not commutative. So, and also notice that 0 is the matrix 0, the 0 matrix. So if we look at this equation, one obvious solution would be if the matrix, the vector v, was the zero vector. So one solution is that v equals 0, 0. First solution. But we want to find more interesting solutions. And so if I rewrite the matrix A as 1, 1, 0, 2 minus lambda 0, 0 lambda multiplied by v is equal to 0. Let me just check that that is actually what A is equal to. Yep, that is what A is equal to. We can then simplify the left-hand side, so it will become 1 minus lambda 1, 0, 2 minus lambda multiplied by v is equal to 0. And if we want the zero vector, the determinant of the left-hand side must be equal to 0. But because we are dealing in the case that the vector v is not equal to 0, for the determinant of the left-hand side to be equal to 0, the determinant of the matrix involving lambdas must be equal to 0. So if we take the determinant of it, so det 1 minus lambda 0, 1, 2 minus lambda, and set it equal to 0, we will get the equation 1 minus lambda multiplied by 2 minus lambda minus 1 times 0 is equal to 0. And this simplifies to 1 minus lambda multiplied by 2 minus lambda is equal to 0. And so the eigenvectors are lambda equals 1 or lambda equals 2. If we substitute these eigenvalues into our matrix and vector equation, we will get that. So in the first case, we'll get that. So if lambda equals 1, we will get that 0, 1, 0, 1 multiplied by the vector v. And actually, I'm going to write the vector v as ab. So multiplied by AB is equal to 0. And so if we carry out the matrix multiplication on the left-hand side, we will end up with B is equal to 0. And so this gives us B is equal to 0. Because remember, the 0 is the 0 matrix or vector. If we set lambda equal to 2, we will get that minus 1, 1, 0, 0 multiplied by AB is equal to 0. And so carrying out the matrix multiplication will give us B minus A. 0 is equal to 0, 0. And so we end up with B is equal to A. So in fact, the vectors that we're looking for are of the form T multiplied by 1, 1. And this makes sense that we'd have infinitely many solutions, because obviously we can have an infinite number of vectors pointing along any line.